Okay, so we got another physics 2 problem where we have this green test charge, or sometimes called field charge. That's this green dot here. We have a positive charge of 6 microcoulombs at 0, 1. So that's going to be what I label 1. And then in red over here, we have a negative 6 microcoulombs. Thank you, Tim. Negative 6 microcoulombs charge at 0, negative 2. And we want to know the electric field at this green point. So how should we do this? Well, first I'm going to write down the equation we're going to end up using. And that will be, I'll do it in orange. Our E field equals K, the magnitude of the charge, divided by the distance squared. I like to write equations out so I know what I'm looking for. That's going to be kind of our master equation, if you will. Okay, make it blue, I don't care. Now I'm going to draw a free body diagram for, I'll do it in green, I guess, for the test charge here. So if we were to look at this green dot, let's start with the first charge. The first charge is positive. Now we always assume that a test charge is positive. Well, like charges repel. So this will be, this is the E field from 1. Okay? Also going to call this theta 1 and this theta 2. So theta 1 goes right here. This is E1 in the y direction. This is E1 in the x direction. So this is going to have a negative component in the y direction and a positive in the x direction. We have to remember that our E field is a vector. Kind of like when we worked with momentum, we had to look at x and y directions. Similar here. Let's see, actually, let me erase this because I'm going to need room. I'll put E1y inside. Okay. So now for 2, what we're saying is right here. Well, those charges are different, and unlike charges attract. So it's actually going to pull it this way. This would be theta 2. This would be E field 2. It has a negative x component. And it has a negative y component. So this would be the free body diagram for test charge. I'm going to box that because this is important. There we go. All right, so now that we have that, let's go look at this triangle a little bit. So we have one triangle right here, which has a height of 2 and an x component of 2. And we'll call this R1. Then we have this guy that also has a height of 2. It shares this side of 2, and we'll call it R2. So first off, let's find R. So let's find R. R1 is going to be the exact same as R2, because those are just how far they are from each other. And using Pythagorean's theorem, that's just the square root of 2 squared plus 2 squared. which is equal to the square root of 8. Or, let's see, that can just be 2 root 2. There you go. So we found R1 and R2. The next thing I want to do is find theta. And for the same reason, we know theta 1 equals theta 2. Now, they have the same sides. The sides are both 2. But if you didn't know, you could do tan inverse of y over x, which is tangent inverse of 2 over 2. And this is 45 degrees. So let's go ahead and box this. Okay. Now, let's look at the forces we have going on. So let's look at your, E field, E, X, we'll say X component. Or better yet, let's do this. X, E. Well, I don't know how to word it, but we'll just say E in X direction. So if we were to summarize the X components, we would have E1X minus E2X. So E in the X is equal to E1X minus E2X by virtue of where they are in our coordinate system. So it's probably worth maybe noting, I'll do it here. This is kind of what we're looking at here in terms of if it's positive or negative. So let's keep going. Our E field in the X direction is E1X, which is going to be K Q1 divided by R1 squared. And then let's see what component that is real quick. Okay, so for the first one, it would be cosine of theta. Well, they're both cosine of theta. Minus K Q2 over R2 squared, also cosine of theta. Now remember, R1 equals R2, and theta 1 equals theta 2. So what does that mean? Everything else is the same, and the charges are the same, right? Yeah, the charges are the same. So your E field in the X direction is going to completely cancel out. Let's box this. Turn on my light. Let me try this. Make it a little nicer. There we go. So we can see there's kind of symmetry here, that they're going to completely cancel if we just look at the our free body diagram. But it's good to work it out. Now what we want to do is E in Y direction. E in Y direction. So E in the Y direction is going to equal, well, they're both negative, so we would just say minus E1Y minus E2Y. Which equals minus K Q1 divided by R squared minus, oops, I forgot. This is going to be sine theta 1. I'm going to call it just theta. And I'm going to call r just r, because they're the same. Over r squared sine of theta. In other words, our E field in the y direction is equal to minus 2k q, doesn't matter, they're the same, r squared sine of theta. And we know this is going to be root 2 over 2. So your E field in the y direction, let's see, the 2's will drop, so you'll have minus root 2, well, we'll have minus k q root 2 all over the distance squared, and then we just have to plug in our values. So let's see what we have. 9 times 10 to the 9th, that's our k constant. Then we have our charge, so that's 6 times 10 to the negative 6 coulombs times root 2 over the distance squared. So that's 2, oops, put it in right, 2 root 2 squared. Okay. So you should get about minus 6750 root 2. Okay? Or minus 9545.94. Now, so let me box this real quick. Okay. Now what we want to do is we want to use the fact that E equals the square root, so this is the magnitude that we're looking for, EX squared plus EY squared, where we know that the X was just 0. So our E field is equal to the square root of EY squared. If we plug that in, you should get your E field is just going to be this squared square root, so just that, which will be 6750 times root 2 newtons per coulomb, or 9545.94 newtons per coulomb. They're both equivalent. And that's our angle. Or, I'm sorry, that's our E field. That's the next part I want to answer. If you want the angle of this, that's going to be tan inverse of EY over EX. Now, e to the x is 0. Oops, let me draw this a little better. Which, although it's undefined because you can't divide by 0, we're looking at the inverse tangent function, and that is defined. And this will be 270 degrees. And that's it. That's the whole problem. So hopefully that helps out a little bit. There was a little bit more to this, so I think it was a good problem to do, and I'll try to do some more here soon.